Hi there, my name is Aaron Lanterman. I'm a professor of electrical and computer engineering at Georgia Tech. In the last couple of lectures of ECE2026, Introduction to Signal Processing, we introduced finite impulse response filters. I mentioned that these had the properties of linearity and time invariance, and that this was a very useful thing, although I didn't really precisely define what we meant by linearity and time invariance. So let's fix that today. We've been talking about discrete time systems that take a sequence xn and output a sequence yn, although the definitions I talk about in this lecture would apply to continuous time systems as well. We're going to focus on the properties of linearity and time invariance. We've previously discussed the property of causality, which means that a system's output doesn't depend on future inputs. It can depend on the past, it can depend on the present, but it doesn't have to. A system like yn equals 0 is a useless nihilistic system, but it is causal. It doesn't depend on the future. It also incidentally doesn't depend on the past or the present. Let's talk about linearity. A system is linear if it has two properties. One is the scaling property. Essentially, if you have an input and an output and you scale the input, you get the same output equivalently scaled. The other is the superposition property. You should be able to take two signals, add them together, and get the same output as if you took the two signals, individually ran them through two copies of the system, and then added the outputs. This is a tremendously useful property for a system to have because it means that if you could write a complicated input as a sum of simpler inputs and understand how the system responds to those simpler inputs, you can figure out what the output is for that more complicated input. You will often see the scaling and superposition properties combined into something like this. On the top, we have two signals, x1 and x2. They're going into two identical copies of the system to get outputs y1 and y2. We take y1, scale it by alpha, y2, scale it by beta, and then we add the results to get an output w. Now in the lower graph, we've swapped the order. We scale x1 by alpha, scale x2 by beta, add them. Then we put that sum signal into a single copy of the system and get an output y. To say the system is linear, we need to show that wn equals yn for all possible inputs x1 and x2. Now, there is a practical nomenclature issue here. What I just described was an ideal mathematical definition. Any system you build ultimately has physical limits. For instance, we'll say that an equalizer pedal that a guitarist might use is a linear system, but that's within reasonable bounds of reasonable input signals. If you put too much voltage into it, you'll eventually clip the op amps inside the pedal and you'll get nonlinear behavior. And if you put much too much voltage into it, you'll actually blow up the pedal. So when we say linear about practical systems, we're usually referring to within a reasonable range of operation. Now, there are systems like distortion pedals that are designed to be nonlinear. Now let's talk about time invariance. If a system is time invariant, if you get a certain output for a certain input, if you took that input and you just shifted it in time, you'll get the same output shifted by the same amount in time. For time invariant systems, it doesn't really matter where you pick your time origin. You can imagine your system that you're trying to test time invariance for and another system that's a simple delay. If the system you're testing is time invariant, you should be able to swap the order. Generally, if you see an n outside of the brackets on the right-hand side here, that's not time invariant. So if I were to say put an n outside of here in front of the x of n, that would not be a time invariant system. That's a time varying system. Now let's consider a system like yn equals x of 3. This is also not time invariant. If I were to take the signal going in and shift it around in time, that x of 3 would be pulling out different parts of x. This is Rhett Scholl, one of my favorite YouTubers and a fellow Atlanta resident, who is about to demonstrate a phasor pedal. A phasor pedal is a linear filter, but the filter characteristics change over time, making a swooshing effect. So this is a time-varying effect. It is not time invariant. Rhett could play the exact same passage exactly the same way again, but it will probably sound different because he'll probably incidentally start at a different place in that swoosh. This is in contrast with an equalizer pedal, which is linear and time invariant, where if you play a chord at 3 o'clock, it will sound the same as the chord you play at 4 o'clock. Let me talk about an issue that is often confusing. Let's consider this system. Y of n is equal to 3x of n plus 5. You might look at this and think, oh, y equals mx plus b. That's the equation of a line. And then you might think, line, linear. But this is not linear in the sense that a system is linear. Think about what that plus 5 is doing. For right now, forget about alpha and beta. Let those be 1. Now, if I wind up adding 5 here, and I wind up adding 5 here, and then I add those together, I wind up with a plus 10 out here. But if I look down here, I add these things together, that goes in, I wind up with just a single plus 5 down here. So I wind up with plus 10 up here, I wind up with plus 5 down here. This system is not linear. If you'd like some more examples of systems that are linear or not linear, or time invariant or not time invariant, I would invite you to check out these lectures from ECE2026 Signals and Systems. These lectures are presented in the context of continuous time systems, but the ideas still apply. You can take most of the examples in these lectures, swap t for n, and get an equivalent example.